Hello student, today we are going to start a new topic which is related to magnetism or magnetic effect of current. Over here we will study the behavior of charged particle when it is placed in a uniform magnetic field. See what will happen, let us suppose this is magnetic field and suppose a charge enters into this magnetic field. Then what will happen? This is basically magnetic field. We say that it will experiences force, and the force will be equivalent to, will be directly proportional to the magnitude of charge. It will be directly proportional to the v sine theta. Means what? The velocity of this charge and the sine of angle it makes with the magnetic field, and it is directly proportional to the strength of the magnetic field. So net force will be what? It is q v b sine theta, or we can write q into v cross b. See, if this charge enters magnetic field parallel to the magnetic field, then sine theta will be 0. In that case, net force will be 0. Force maximum will be q into v into b when it enters the magnetic field at 90 degree. Why? This is sine 90 is going to be 1. And similarly, for minimum, force minimum, it will be 0 when theta is going to be 0. And in that case, sine 0 is what? 0. See, we can define magnetic field also from this formula. What is that? We know that it is what? Force equal to q v b sine theta. B is what? Force upon q v sine theta. See, magnetic field, strength of magnetic field is what? It is Tesla, and force is what? Newton, and the charge will take is that 1 coulomb. Velocity is, let us suppose it is 1 meter per second, and it is entering magnetic field in making angle theta 90 degree. So this is 1. What we can say is that magnetic field is said to be 1 Tesla if a charge of 1 coulomb moving with velocity of 1 meter per second in a direction perpendicular to magnetic field experiences a force of 1 Newton. We will say that magnetic field is said to be 1 Tesla. This strength of magnetic field is 1 Tesla. If a charge of 1 coulomb enters the magnetic field with a velocity of 1 meter per second in a direction perpendicular to magnetic field, then and it will experience a force that is 1 Newton. Then the strength of the magnetic field will be 1 Tesla. Now we will try to study what is the force experienced by charged particle or force experienced by current carrying conductor placed in the magnetic field. See, we will study what is the force experiences by charge particle placed in uniform magnetic field. See, we see that, let us suppose this is a conductor and it has been placed in the magnetic field. Let us suppose it makes angle theta with it. This is magnetic field, and this is basically a conductor, current carrying conductor basically. See, we say that we have to find what is the force experienced by this conductor when it is placed in a uniform magnetic field. See, we see that conductor is basically constituent of what? There is a large number of particle, basically charge particle, which will experience force. What we'll do is that we have studied in the earlier part that force experienced by charge is equal to what? E into V cross B. See, what we will do is that we will determine force experienced by each electron in a conductor. First, see, what is this? Force experienced by one electron in a conductor. We know that this is force experienced by one electron. This is the charge on one electron. We can write minus E over here. Vd is basically drift velocity. Means it is the average velocity with which electron is moving inside a conductor. V is the strength of magnetic field. And we know that in a conductor it is not that there is only one electron. It contains large number of electrons. So total charge contributed by all these electrons will be how much? It will be equal to N. This is A is the what? Area of cross section of the wire. L is the length of the wire. N is the number density, and this is charge on each electron. See, what is this? N is what? Number of electron per unit volume. Then we have what is this? A is what? This is area of cross sections, and L is what? Length of the conductor. Length of conductors. And E is the charge on electron. Charge on electron. So what we have? So total force due to all this charge will be equivalent to what? Force will be equivalent to Q into Vd cross P. So what do we have? This is Q is what? N into A into L into E into Vd cross V. Okay, what is this? This is force due to all the charge. Due to all charge in a conductor. So what we have? We know that over here we have like we can simplify it out, because we have like we had derived earlier on that I is basically equivalent to NEAVD. Current inside a conductor is equivalent to NEAVD. So what we can replace this NEAVD by I. So what we are getting? This is V, this is I into L. Or we can write B I L sine theta, or I into L cross B. So this is the force experienced by the current carrying conductor placed in a magnetic field, and we can see that force will be maximum, that will be equivalent to B into I into L. And suppose when angle the magnetic field makes with the current carrying conductor is 90 degree, in that case force will be maximum, and force will be zero when current carrying conductor is parallel to the magnetic field lines. Angle is zero. In that case, we'll have force on a current carrying conductor will be zero. Now we will move on to next topic, that is force between two parallel current carrying conductor. we have to go for force between two parallel current carrying conductor. What is that? Let us suppose current over here is I1, current over here is I2, and distance between them is like R. The topic is what? Force between two parallel current carrying conductor. See, in the last topic what we had studied, that force experienced by a current carrying conductor is equal to B into I into L. See, over here what you see that, see, let us suppose this is a current carrying conductor AB, this is CD. Let us suppose a point P, this point. So what we have, magnetic field produced by this conductor at this point P will be what? Magnetic field due to current carrying element AB at point P. See what will happen over there. See, basically this AB is what? It is basically infinite conductor, and the strength of magnetic field at this point P will be what? It is equivalent to V0 upon 4 pi. This is 2 I1 upon R. This is the strength of the magnetic field produced by this conductor AB at point P. And what we have to find next is what? Suppose that is this conductor, this is CD, is placed in the magnetic field of AB, then force will be what? Force experienced by conductor CD in a magnetic field of AB. See, it will be what? Force will be B1 into I2 into L. B1 is what? We have like V0 upon 4 pi. This is what? 2 I1 upon R. This is the strength of magnetic field. This is I2 and this is L. So what we have? We get force acting per unit length by this conductor will be equivalent to what? V0 upon 4 pi into 2 I1 I2 upon R. This is basically length L. See, on basis of this definition, we can define what is 1 ampere. What is that? See, we have like, let us suppose this is 1 ampere. This is 1 ampere. I2 is also 1 ampere, and the distance between them is 1 meter. See, in that case, we have to define ampere. See, we see there, this is 1 ampere, this is 1 ampere current, and distance with them is 1 meter. So force will be equivalent to what? V0 upon 4 pi into 2 I1 I2 upon R. See what we have? This is what? 10 to the power minus 7. This is what? 2, this is 1, 1, and this is 1. So what we are getting? 2 into 10 to the power minus 7 Newton per meter. This is what, because this is 4 acting per unit length. How to define that out? See, what we'll do is that we'll say that 1 ampere is that current which, when flowing at a distance of 1 meter apart, experiences a force of 2 into 10 to the power minus 7 Newton per meter on each other. So we have learned that basically what is the force experienced by a charged particle when it is placed in the magnetic field. that is basically force equal to Q into V cross B. Then we studied what is the force acting on a current carrying conductor placed in the magnetic field. What we did was that we calculated force due to one charge. Then we calculated the, because conductor is just not made up of one charge, it constitutes large number of charge. We calculated all the charge, and that was equivalent to N into A into L into that E. That was total charge, and the force experienced by total charge was equivalent to B into I into L. What we did was then in that derivation we replaced I by NEAVD. So we made it short. Then we came to force experienced by two parallel current carrying conductor. Over there, what we did was that this is AB. What we did was that we calculated the strength of magnetic field produced by this conductor at point P. And then what happened? We already know that force experienced by a current carrying conductor in magnetic field. What we did? That is force equal to B into I into L. The contribution of magnetic field to AB is what? Mu naught upon 4 pi 2A upon R. And since this is the current carrying conductor placed in the magnetic field of this, what we have? This is B1 into I2 into L, and we got mu naught upon 4 pi 2 I1 into I2 upon R. And generally we see that in CBSE examination, after deriving this, they do ask definition of ampere on the basis of this. What we did was that we took, let us suppose I1 is also 1 ampere, I2 is also 1 ampere, and distance between them is 1 meter. Then we say that 1 ampere is that current which, when flowing at a distance of 1 meter apart, experiences a force of 2 into 10 to the power minus 7 Newton per meter on each other. That's all for today. We'll meet in the next class. Thank you.